So today we're looking at particle motion problems with parametric equations. So in this example, it's a word problem with several parts. There's actually more parts than this. We do have a D and E, so let me pull that up. Okay, so there it is. We have our example, and we have parts A through E. And the given information. A particle moves in the xy plane so that at any time t is greater than or equal to 0 seconds, its position, the ordered pair x comma y, is given by x equals the ln of the quantity t plus 1 and y equals t squared minus 1. So there's a couple things that are being described here. So if we're moving a particle in the xy plane, it is typically meaning that we are using parametric equations. So we would have an x of t and a y of t, and that is given to us. Sometimes it might not be a t, it could be a theta, but in this case it is t. It indicates that t is greater than or equal to 0 seconds, which makes sense because time can't be negative if we're using t. And so let's take a look at what we're saying in part A. So in part A, it says, find the position of the particle when t is equal to 1. Well, the position is x comma y, and we don't know what that is. So we need to figure that out. We need to figure out it's x and it's y, and they tell us when t is 1. So we're going to replace t with 1 in the x equation and t with 1 in the y equation. So if I do that, I'm going to get an exact location of the ln of 2, 0. Okay. Plotting that's going to be a little bit difficult, so it would be best if we see what our final answer is. So we're going to round to 3 decimal places for the ln of 2, and that is about 0.693. And so that would be what we would get if we were to graph it. All right, so that's A. A is done. So let's take a look at part B. Write the corresponding rectangular equation for y in terms of x. So this we do by eliminating the parameter. So let me get rid of the writing here, and let's take a look at B. It's actually just one example today, so I could just write example. All right, in any case, we have 2 parametric equations because it has to be a set. Since there's more than one t in the y equation, we're not going to use the y equation, and we typically use the x equation to solve for t. So to do this, we're going to raise x to be the power for e, and we're going to raise ln of the quantity t plus 1 to be the exponent for e. And it leaves us this expression. So t is actually e to the x minus 1. Great. We're going to go to our y equation, and we're going to replace t with this e to the x minus 1 quantity. And we would have to square it and subtract 1. So let's do that. There's a lot of terms I'm going to have to squeeze in here. So, you know what? I'm going to bring this back around here. A lot of looping arrows today. That's all right. So e to the x times e to the x is e to the 2x. And your outer and inner terms are the same. So this a negative 2e to the x, and negative 1 times negative 1 is positive 1. So this becomes 0, and we're left with a final answer that y is the exponential equation e to the 2x minus 2e to the x. Beautiful. Now we're up to part C. So in part C, it says at what time t is the particle 8 units above the x-axis. So let's think about this. If we were to draw out our coordinate plane where the particle is moving, we can see our x-axis is here, and we want 8 units above. So it could be this point here, or that point here, or this point here, okay? But what is consistent with all of these points, regardless of what the x value is, the y value is 8. So with that being said, okay, in C, what we need to do is make y equal to 8 and try to figure out what t is. So we have an equation for y in terms of t. So we're going to replace the y with 8, and we're going to solve for t. So we have a polynomial equation, and we can factor and set each factor equal to 0. And we get t is -3 and 3. Hold on. T is -3? Nope. We're going to reject that because t has to be greater than or equal to 0. It is time. So our answer here is 3. That is what was in question. So when it was 3 seconds. All right. So let's take a look at part D. So in part D, it asks at what time is the particle on the y-axis. So similar to the last one. Okay, so let's think about it. It's got to be on the y-axis, this right here. This is where x is equal to 0. Every point, okay, x is going to be equal to 0. So we're going to replace x with 0 in this equation and solve for t. So we need to know at what time t. And so we use e on both sides, and we find out that this is when t is equal to 0. It just worked out that its answer is 0 seconds for part D. And E. So in E, it says, at what time t is the particle 2 units to the right of the y-axis? So you're going to notice with a lot of these word problems, you have to try to figure out what's being asked of you, what would make sense, and use what we learned in math already. Keep in mind everything we looked about particle motion and parametric equations. If you need to actually graph out the path, then create a table of values and use the half intervals. All right, E. So 2 units to the right of the y-axis. 2 units to the right. That's when x is 2. Doesn't matter what point would be plotted, x would always be 2. So we're going to replace x with 2 and solve for t. So this isn't as straightforward as the last one because t is e squared minus 1. Okay, so if we need to know how many seconds, t is approximately 6.389 seconds. Thank you to our graphing calculator. I'm going to abbreviate seconds here. That's a decimal. All right. So I think everything was explained for this type of problem. Again, I mentioned about graphing and tables and stuff like that. So keep that in mind when you're trying to approach these problems. You do know about your coordinate plane and all other things relating to mathematics. So good luck.